Now let's talk about deleting a particular node from binary search tree. So we'll have operation delete, and I will give the address of a node. Okay. So here we are assuming that we have already located the node that we want to delete. Okay. So sometimes you might want to delete a node that contains a particular value. In that case, we are expecting that first you have performed the search operation and you have received the address of the node, and now that you have the address of the node, you want to delete it. Fine. So that's the way we expect our delete operation to work. So let's consider the first scenario. We have to consider these three scenarios. First, when the node that we want to delete is a leaf node and it doesn't have any child. Second scenario, when the node that we want to delete has only one child, either left child or right child, but it doesn't have two children, just one child. And the third case is the scenario where a node that we want to delete has two children. Okay. So let's start with the easiest case. Okay. So I'll say that if node dot let's have a function called child count. Okay, if node dot child count is equal to 0, if that's the case, then what would I do? Then I would just delete the node. Okay. And there is no extra processing required. Okay, we'll come to it. What do we mean by just delete the node? Okay, and then we'll return. Okay. However, otherwise, if we observe that node dot child count is equal to 1, if the node has just one child, in that case, what we'll do? In that case, we will replace the node with child, and again we'll come to it. What do we mean by it? And otherwise, what is going to happen? Otherwise, we know that the node has exactly two children. Okay, so else we know that node has two children, and if a node has two children, it means that it has a left child as well as right child. And it's not necessary that they are just nodes, they could be subtrees on their own. Okay, for example, if I talk about node 100, its child count is 2, it has two children, but they are not just nodes, they are subtrees. Okay, so a node can have two children, and those could be the subtrees on their own, they would be binary search trees on their own. So if node is a leaf node, so again let's go back to our example tree. So if I want to delete any of the leaf nodes, 25, 60, 250, 400, okay, deleting them is easy. All I need to do is I need to change the pointer stored in my parent. I need to store the parent pointer stored in my node. Okay, so deleting the node would involve what? Okay, I will say that get the parent. Okay, so what is meant by just delete the node? I will say that the parent node is equal to node dot parent that I want to delete. And now I'll ask question, is the current node a left child of parent or right child of parent? Okay, so I'll ask question, if node is equal to parent dot left, if that's the case, in that case what will I do? I will say that now parent dot left is equal to null. Otherwise, I know that the node that I want to delete is the right child, and I will say that my parent dot right equal to null. I'll assign this value. Okay, so that's the block I need to put in place here, and then of course I have to set the node dot parent equal to null. okay, for this. So it becomes separated from my tree, and then I will return the node. The node is now isolated from the tree, and I will return it. Okay, so that's what is required if you want to delete a node which is a leaf node. Fine. Now let's think, what should we do if the node that we want to delete is having just a single child? In that case, again we have to do something similar. Okay, so I'll leave these things as a bit of exercise to you. Okay, so what we really need to do is we need to take out our current node, and then whatever child it has, it might have just the left child or just the right child, take that child and we have to attach it to the parent, and we have to attach it properly. We have to ask the question that original node, was it a left child or a right child, and accordingly we have to attach this particular child to the parent of the node. Okay, so I leave this as exercise to you. Try on your own. If you cannot do it, we'll discuss it during the interaction session. But now let's come to the most tricky case. The node that we want to delete has two children. So if you notice the binary search tree, see, deleting any of the leaf node is straightforward. If I delete any of the leaf node, still the resulting tree will be a binary search tree. If I delete any node that has only single child, so let's talk about a scenario where I have just the left child. Okay, so if I want to delete 80, I can remove 80 and replace it with 60, and still my resulting tree is a valid binary search tree. Okay, do we have a case where we have only right child? We have a case here. Okay, so 200 has no left child, but it has only right child. So if I want to delete 200, I can simply remove the 200 and replace it with 300, and still the resulting tree will be a valid binary search tree. But the tricky scenario is that if I want to delete a node that has both left children and right children, both left and right child. So for example, 40, it has 25 and 80, or 100, it has 40 and 200, or 300, it has 280 and 400. So if I decide to delete 40, who should replace 40? If I decide to delete 100, who should replace 100? Is it 40 or is it 20? Okay, that's the question that we have. Okay, so in that case, what we would do is, we already know how to find out successor. Okay, so what I will do is, I'll say that I'll call it the next node equal to the function that we just defined, successor for a node. Okay, I'll call that function, I'll call the successor of the current node, and note that current node has left child as well as right child. So if right child is present, then the successor is always located in that right subtree. Okay, so we'll always hit this case here. So now I get the successor, which is next node, and then what I will do is I will swap nodes. Okay, so I'll swap two nodes. Which are those nodes? The current node that I have and the next node that I got. So I'll swap their positions in the tree, and once I have done that, actually my tree will not be a valid binary search tree. Okay, after this swapping. So after I have done that, what I will do is I will go and delete the particular node that I'm talking about. So after this, I will delete my node, and once I delete, I will get the result. So I'll return this result. Okay, so let's see how it works. Okay, for the case where we have a node with left child as well as right child. Okay, so let's try to delete 100. Okay, so deletion of the 100, we'll ask question, 100 has 0 children? No. 100 has only one child? No. Otherwise, now we have to go and get the successor for 100, and we have seen the successor for 100 is 200. Okay, so I'll keep track of this. Okay, so now successor I have got is 200, so my node is 100 and my next node is 200. And now I'm going to swap nodes. Okay, so what do I mean by swap nodes? I should exchange these nodes. So if I swap nodes, how my binary search tree would look like? So now 200 is going to replace the 100. So 200 is going to be my root and my right child will be 100 and my left child will be the original tree, right? 40, and 40 has 25 and 80. And then 80 has 60 as the left child. And for 100 I will have 300 as the right child. And 300 would have 400 as the right child. And the left child of 300 is 280. And left child of 280 is 250. Okay, so once I swap the nodes, that's the tree I will get after swapping the nodes. And this is not a valid binary search tree, because if I go and look at the left of 200, I have value less than 200. If I go and look at the right of 200, the value is also less than 200. Okay, and the problem is precisely caused by the swapping of these two nodes. But the next thing I'm doing is delete node. I'm calling it recursively. And now what is going to happen is, whenever I call this delete node operation, it will result in 100 being a node that has either just one child or no child at all. So it will have these two cases. Okay, because I have found out the successor, right? So successor is the rightmost node in my subtree. Successor is the leftmost node in my right branch. I'm sorry. Okay, so given a node, if I want to locate the successor, I will look at the right subtree and it is the leftmost node in that right subtree. That's my successor. So by definition, if it's the leftmost node, it doesn't have a left child. Okay, it might or might not have right child, but it definitely doesn't have a left child. So we have converted the deletion of 100 to a case where now we have to delete a node that has either one child or no child at all, and that can be done easily. So in this case, what will happen is 100 will be simply replaced by its child, which is 300. Okay, and once I do that, this becomes a valid binary search tree, and I'll be returning the address of the node 100. So this deleted node can be used by client code for whatever purpose that they want. And now if I try to analyze the time complexity of this operation, if the node has no children, in that case it requires only constant time effort. If the node has a single child, even that would require constant time efforts, but bit more than this. I have left this as an exercise for you. However, if node has two children, then finding out the successor might require the time which is proportional to the height of the tree, and swapping of the nodes would require constant amount of time, and the deletion called recursively would always require only constant amount of time. Okay, so that's why the deletion of node in the worst case would require theta h time, where h is the height of the binary search tree. And in the worst case, remember, height of the binary search tree can be equal to the number of nodes in my binary search tree.